All right, guys, we're going to talk about this Redline standalone single loop digital controller here sitting in between these two meters. The meter you see on the left is our input from our transmitter, simulating like a level transmitter out in the field. The meter on the right is the output to like our control valve, okay? So right now I'm just doing basically the application that we got for our tank on our trainer. That tank is about 3 foot tall, and the calibration range that I had set that up for with that DP transmitter for head pressure level was from 6 inches of water to 24 inches of water. Okay, so 6 to 24 inches of water is the range. So what we're going to do here is we're going to take a look at the effects of an error on a proportional setting. So what I've done over here, this gets a little bit difficult to see and actually understand here. It's even worse when your screensaver goes on. So what we've got here is we've got a software called Crimson 2.1 for panel meters. And there's a ton of settings in here that we can access, and I'm going to try and make this as simple as possible here to give you guys an idea of what's going on. This controller can be really complicated. It can have multiple different PID loops that we can trigger to run depending on what's going on. However, at the end of the day, we're just going to focus on PID number 1. And you can see there that the proportional band setting is 18. Well, this controller is just a little goofy in the fact that it wants to know how much change in your process variable it takes to make a full-scale change in output. And that's really what proportional band is about. What percent of change does it take to make a full-scale change in output? Well, a proportional band of 100% would say that I need 100% change in my input to make 100% change in output. Well, 100% proportional band is a gain of 1. That means for every 1% change in input, I'll get a 1% change in output. Well, with a calibration range of 6 to 24 inches of water, the difference between those two, or the span, is 18 inches. So I've literally set this at a gain of 1, proportional band of 100%, by saying that it takes 18 inches of level change to make 100% change in output. Okay, so at the end of the day, that's a 1-to-1 ratio, or proportional band setting of 1. Now, if I was to change that to say it's going to take 9 inches of change to make 100% output change, that means I only have to move half as much on the input to get a full-scale change in output. So later, we'll check this out. We'll come in here and change this setting to 9, and it'll essentially be a 50% proportional band at that point, saying it only takes a 50% change in input to make 100% change in output, which essentially inversely proportional would mean that we have a gain of 2. So whatever error we see, we multiply times 2, and that's what would affect the output. Now, that being said, we are going to go ahead and go over here and take a look at these meters. And I told you that I have a gain of 1, okay? Or a gain of 1, 100% proportional band, right? So what I'm going to do is I'm going to change my input by 10%, okay? So on my input side, a 10% change would mean that I would ramp this thing up to 10% of a 4 to 20 milliamps. So 4 to 20, the span of that 16 milliamps, and 10% of that would be 1.6. So if I go up by 1.6 milliamps here with a gain of 1, or a gain of 1, I am going to have an output change by 1.6 milliamps. So let's go ahead and test our theory here, and I'm going to go up to 13.6. All right, and that's a 10% change. You can see here where it's 60% of our signal. Now, if you come over here and take a look at this, we would expect this. Now, this is This is reverse acting. That means that when the process variable goes up in direction, that means that the output goes down. Now you've seen that they were both at 12 milliamps when we started, and we went up with the process variable, so we went down with our output. Now you're saying, well, that isn't exactly 1.6. Well, no, it's not. It's close. I get it. Okay, we should be sitting at 10.4 milliamps. We're pretty close. All right. So at the end of the day, it could either be this meter or it could be the output card on the PID controller, but I'm betting it's this meter. This is my own personal meter. You can see it's got sheetrock mud on it. It's been beat around. This thing hasn't been calibrated for probably a decade, so it may be off just a hair. We're not going to worry about it. At the end of the day, we changed by 10% up here, and we went 10% down here, okay? So I'm going to go back to the set point, which is actually, you can see here too, by the way. You can see that when we went up, our actual measurement went up as well by the 10%, okay? So our PV is at 16.8 and our set point's at 15. That generated a 10% error. We got a gain of 1 times the 10% error, and we have got a change in 10% on the output. So we're going to go back to 12 milliamps. That means I got a 50% input, okay? 50% input. Now if you remember that formula, V sub O, your valve output, is equal to P sub G, which is your proportional gain. We got a gain of 1, times your error. So right now there's no error. 15 is the set point, 15 is our measurement. So our output is sitting at 50%, right? V sub O is equal to P sub G times the error plus 50%. So we've just proven that right there, that our output's sitting at 50% when our process variable is at set point. So we just proved that formula, right? And we actually proved the formula when we made the 10% error, because we took and we subtracted 10% off of that 50% signal, and we ended up at 10.4, which is essentially a 40% signal on a 4 to 20 milliamp. Now this time I'm going to go back and start a new video, because I don't want these to get too long, and we're going to go ahead and make a larger error. So I'm going to shut this down and start a new video.